Okay, so when we were working on the first couple of pages of Chapter 11, Section 6-7, um, we were noticing how the X scale for your data values is divided very specifically to having a mean in the middle, and then one standard deviation, two standard deviations, three standard deviations, high and low. That's how it always is. And instead of trying to explain over and over again that these are, this is 85 is a one standard deviation on the low side of this scale, you can call it a z-axis. Okay, so if we add some numbers to it, we're kind of standardizing the normal distribution by calling where the mean value sits as a 0 on a z-scale. So some people put their z's above their x's. Some people put just kind of a z right underneath the other one and say, okay, the 100 is at a z-score of 0. This 85 here is a z-score of -1. That tells me that the 85's one standard deviation lower than the mean. The 70 is two standard deviations, three standard deviations lower than the mean. So up here, this is a +1, 2, 3 on the z scale versus the x scale. So these are data values. These are the corresponding z values that go with these x values. So we're still talking about the same kind of area probability of numbers falling in here. And half of it is still 0.5. The scale is a 1 because it's disease now. They're saying the probability or cumulative area close to positive or negative 349 is kind of almost 0 because this, see how little shading is down there? Okay. We had some numbers in one of the sections. It kind of came out to like that. And we just said that's approximately a 0. So it's not for certain. So there still is a probability that, it's extremely low. In fact, it's close to 0 that a data value will fall over here somewhere on the extreme ends, but it is possible. That's why this line never crosses the x-axis. So when we want to convert an x value score to a z score without doing the sketch of the scale, you can just put the x value here, the data value here, subtract its average, the mean value, and divide by the standard deviation, and you will get its matching z score. Okay, so let's do some of those. For example, Tina scored an 80 on a history test. And there was also a biology test. And her individual score was an 80 out of 100. And her biology score was a 75. But for the history, the mean was 70. There's your X bar. Okay. And for the biology test, the mean is also 70, but the standard deviations are different. The history test had a standard deviation of 10, so 80, 90, 100 on the upside, 60, 50, 40 for the X scale for the history test. For the biology test, though, the standard deviation was only 2.5. So this is 72.5 Add another 2.5 is 7.5, add another 2.5, and that is 77.5 for 3 standard deviations. 70 minus 2.5, minus 2.5, minus 2.5 gets the whole scale in for the x values. And then if you want, you can draw your z's underneath. So there's your mean, 1, 2, 3 standard deviations, -1, -2, -3 standard deviations. Same with this one. Don't forget that 0 in there. All right. What was the question again? Let's see. She got an 80, so she was here. And on her bio, 75 is here. On which test did she do better? I think that's a confusing question. She obviously got an 80 on the history and a 75 on the bio, but which test was harder for the whole class? Well, even though your averages are the same, look how hard it was to get over an 80 in this very hard bio test. Very rare, very extremely high value. So most of the class, 99.7% of the class, fell above a 62 and below a 77. So compared to the rest of the class, she did better here. What is her z-score? Well, this corresponds to a z-score of 2. This corresponds to a z-score of 1. We can also do the math to back that up. Remember, a z-score is our value minus our average over our standard deviation. So this was an 80 minus the 70 over 10 for this, right? This was x bar was 70, our s was 10. So this is going to be 10 over 10 or 1, and that's what we got here graphically. So that is correct. And this one had an S of 2.5, so our Z would be her score. Minus the average over the standard deviation. You're going to get a 5 over 2.5, which is a 2, which is what we get, what we see here. Okay, so better would be if you're talking about higher z-score, she did better on the biology test. Okay. And then we can take that same formula here and multiply both sides by s, and then subtract our mean, put it on the other side, and you get this formula. So if we're looking for a z-score here, we're using this. If we're looking for the data value that matches that z-score, this is the formula we can use. Or you can just be careful doing your math doing it this way, but that's one is a lot easier to do. So let's try that. All right, a veterinarian records the weights of the cats in the clinic. And they found to be normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. Okay. All right, so our X values, our data values are here with an average of 9 pounds. All right, find the weights that corresponds to the following Z scores. So look at this one here. I have a z-score of 0. They want to know how many pounds that corresponds to. 9 is obviously the answer, but we can do the math. That'll be 9, according to this formula here, 9 plus the z-score of 0 times the standard deviation. That's going to give you your 9, because that's 0, right? 0 plus 9 is 9. So let's find these other ones. We have a negative 0.44 z-score. So if this is kind of like 0.5, negative 0.4 is kind of like here, negative 0.44. So it wants to know the value that is equivalent to a z-score of negative 0.44. Well, we want to use this formula here. So that would be our x bar, which is 9, plus our z, times our standard deviation. That's going to give us our x. That is going to come out to, well, what do we expect it to be? If that's 7, that's 9, that's 8. We expect it to be a little higher than an 8, and actually it comes out to 8.12. So if a cat has a z-score of this is how many pounds they are. And this immediately tells you how average this cat is. The cat with a z-score of 0 is 9 pounds. So if this is 8.12, it's slightly under. That's what the negative tells you. It's under the average. And then just kind of like, slightly under. So 8.2 seems reasonable. All right. How about this cat? Definitely is on the heavy side because it's almost 2 on the Z scale here. 1.96 on the Z scale. So quite chunky. Let's see what this is going to turn out to be. This is the average, which is 9, plus the Z, which is 1.96 times the standard deviation. What do we expect it to be? It's really close to 13 pounds is what we expect it to be. And mathematically, it comes out to 12.92 pounds. So very close to 13. So whether you have the X values or the Z values, you can use them to find each other, whatever's missing. Okay?